defines the set. And of course, we're going to have sets of strings like this one here with Mary and contrary and quite. Okay, but of course, you can't have Mary show up twice. So that example there is an incorrect set. So you'd have to just knock out one of the Marys and then we get back to a proper set. Okay. So now how are we going to model this? So in Java, the set interface turns out to be the same thing as a collection interface. So we've already seen it, but now we want to exercise it for sets. Okay. Now, the set, of course, is not supposed to have duplicates, but that's not actually expressed in the API. But it's documented in the API documentation. Okay. So anyway, what we're going to be looking at are the major implementations: the tree set and the hash set. Okay, and they both check for duplicates in the code in their implementing code. So in tree set uses the comparator that you must have in order to use it, and that's for the elements. And hash set uses equals. Okay, so that's how they check for duplicates. And of course, you're supposed to have equals and compare to be consistent, but in the actual code only uses compare to in tree set. Okay. And of course, we also have to have hash code, but we'll go over these requirements. So here's the collection interface. Well, it's not as complete as the previous one, but it has the major methods in it. So you can see that we can tell how many elements there are in the set. We can tell if the set's empty. We can see if it contains any particular object. And we can add objects and we can remove objects. And we can clear everything out in one call. And we can iterate through the set. Okay. So you can see that this is just the same as a collection interface. And in fact, there are a couple more methods that we listed when we did the collection interface, and they'd be here too. And in fact, even that wasn't complete. We're going to come back to look at other methods, more advanced methods. Okay. So here's the way it works. The set interface extends collection. This extends is how one interface is based on another. So this really means that they have the same API. Okay, so we're going to see, in fact, some more powerful methods in the future. We're going to see how we can do set union, intersection, and difference by using calls into the full API here. But tonight we're just getting started looking at the more basic things about it. And of course, in the more complete API that we looked at before, it did have ways to put the collection into an array. So that was missing from the one we just looked at. Okay, so in addition to the API, we have these guarantees by the documentation, and they are based, of course, on the proper equality testing of the elements. But once you have a JDK set, then you have real equality set testing by sets. So if you have two sets, S1 and S2, you can ask whether, in fact, they are the same set by doing S1.equals S2. Okay? So if they are, if that comes back true, that means they have the same elements based on the element equals method. Okay? So it, of course, does depend on that. And you can see that if you look at the textbook, we do have a set API on page 489. And it's, if you look at that API, it's much like the one we just looked at. which is, of course, a subset of the full one. But strangely enough, they don't offer any concrete classes for for their set API. It's one of the few cases where they have an API, but no implementation. But if you read the text, you find out that you're supposed to use one of their ST classes and simply ignore the values. So you're using the fact that the domain of a symbol table must be itself a set. Okay, so that's how they get around it. So we're kind of doing the opposite approach. We're going to look at sets first because they are fully supported in JDK. And once we have that settled, then we'll look at maps, which are like the symbol tables. Okay, so here's a simple example to use a tree set. You can see we can set up a tree set and we can just call it a set because, in fact, we could do the same code with a hash set and it would work it would give you exactly the same results, except possibly for order. Okay. So as usual, we have to import the classes that we need to use, and then we're just having a main in here. Create a new tree set, and if you wanted to, you could reverse it this way, but let's not worry about that. You add various strings, and then we can use the enhanced for loop to print everything out. Or even easier than that is you can just print the set object and you'll get basically the same thing. It'll go through and print out, call the toString method on all the elements for you. Okay, so it's very nicely implemented class. So this, of course, this enhanced for loop is based on an iterator that's hidden away. A hidden iterator is used by the system here. Any questions on this? Okay. Okay, so we actually end up seeing that these come out in order, in string order. So you might worry that a set isn't supposed to have order in it, and here we have an ordered set, but it doesn't really hurt us. So it's just an extra feature. In fact, you can even call it a sorted set. That's another interface in JDK. But normally we just call it a set and just ignore the order if we want to. So the tree set is a very good implementation, and it's of course hash set is even faster in some cases, but tree set is just a little bit slower. We'll look at the performance eventually. Any questions on that? Okay, so here's another little example. You can see that if we use these JDK classes as elements, everything is really easy because they all have equals and hash code and compare to all implemented for us. Right? So here we have a new hash set, the same thing as the tree set before. Okay, so we have, this is just a typo here. This should be, the formatting isn't great. Okay. So this is using the hash set of string. Okay. And of course we can add another, if we add HAL a second time, it won't fail or anything, it'll just quietly ignore the addition. It will just, because the set can't have any duplicates. Okay, so far we've looked at the simple cases where we're using the JDK types for elements. So What happens if we use our own class for the element type? Well, in that case, we have some responsibilities. We have to make sure that the methods that the implementation is going to actually use to run its show are in consistent state. Okay? And so they have different, the two implementations have different requirements. The hash set says that equals and hash code must be consistent. And what does that mean? That means that if A equals B by the equals method, then the hash codes have to agree. But it doesn't have to work the other way. You can have two different objects that not equals that have the same hash code. Okay, so it just has to work this way. That if there's true equality, then there's hash code equality. Okay, so the hash, remember, a hash code takes an object and just turns it into a number somehow. That's there's a little bit of coverage of that in the homework. Okay. So that's what you have to have for hash set. And for tree set, you have to have a compare to method that's implemented, or there is another way of providing a comparator when you create the set. But I haven't written that in these slides yet. So what we're assuming at this point is that you have equals and compare to for the elements. So if the A equals B, then the compare to will be 0. And in fact, the tree set will never call equals in its work. It will always call compare to. Okay. Any questions on these? So this is the elements that this is requiring. Okay, so we've talked about the object methods and how they're inherited. And that means that since the object class has equals and hash code implemented, any object has equals and hash code. You don't have to implement equals or hash code in your Java class. You'll get the one from object. Okay? And they're consistent in the sense that's needed for the hash set. So equals and hash code are consistent. And so if A equals B, then the hash codes are equal. Okay? So you see, for free, then, if you have a simple Java class like bank account, remember a bank account, it doesn't have equals or hash code, so it would get them from object. So that's great. We can make a hash set of bank account without any extra work in the bank account class. But it does have a downside. Okay, because object doesn't know anything about the bank accounts, it has no way of checking the IDs or anything like that. All it has are the reference addresses, the locations in memory of the objects, and that's what's used. So equals just means they have the same memory address. Okay, so you could have two representations of the same bank account that are sitting in different places in memory, and yet they would be considered different by this testing, and that's not ideal. So there's an incentive for us to implement our own equals and hash code for bank account, so that we can make two bank accounts that have the same ID, two bank account objects for the same ID. We can say they're equal instead of having to say they're not equal because they have different memory addresses. Okay. So that's what I hear. If we want to avoid duplicate names of person, if person is, or duplicate IDs of order or bank account, we need to code equals and hash code. Okay, so this is sort of a pain, but something you need to know to do this right. And it turns out that coding equals is tricky. So what you do is you find a known good code, such as the code on page 103, and change it to meet your needs. Okay? You can also look at this article. I like this Geeks for Geeks. It has a lot of good little write-ups of things, and they explain this too. Okay. Any questions on this? This basic setup. Okay. So here shows the remarkably difficult code for equals, right? In the case for an order. So this is an order, and like many Java classes, it has a unique identifier in its fields. Okay, and it can have other instance variables, but they would just take up more space on this slide. It's complicated enough. So we're just looking at the unique identifier. It probably has part numbers and things like that, but it doesn't really matter. And it has to have a getter for the ID, and probably getters for other instance variables. But what we want to look at now is the equality. We want to make equality based on this ID value. So if you have two order objects for ID 100, we'll consider them equal. So how do we do that? Well, as I said, we really should copy other code. So if you look at page 103, you'll see this basic code for a different object. So this is for performance sake. If the two objects that we're talking about, the current one, this, and the other one that's coming in as the other object, if those are identical, it's the same object, so you can return true right away. So you could avoid this because it will answer right in this case with the rest of the code. But I'm following the book on this. Okay, and then if this is more important, if check for null, the other object coming in is null, then there's no way there could be an equality because this one is a real object. So that should return false. And now we have to get down to the case of whether the IDs match or not. And in order to see the ID, we need to have, we need to know what class it is, something about the class, So all we know is its object. So we don't know any way of getting it to directly to find its attributes and find out if it has an ID attribute. So of course, so the simplest solution to this is to simply check if the class is correct. If the other class is the same as this class, we want to go on. So if they're different, of course, that means that they can't be equal, so we return false. So this seems like a very strong condition. Maybe, in fact, it is possible to weaken this. But this is the simplest case, to require the classes to be the same in order to go on. Once we know the classes are the same, then we can take this object and cast it over to an order object. Okay, so that's what this is doing, casting it to an order object, knowing that its class is order. So this won't blow up on us. Okay. And then once we have this other one as O, we can look at its ID. So it's just O.ID. So we're checking here whether the IDs are equal. If they're equal, then of course you return true, and otherwise you return false. So we need to do all this work to do a proper job of checking for equality of these objects. Okay. So compared to this, the hash code is easy. If you use this trick, the trick is, well, we know that the integer, we have an int ID, we can convert it over to an integer, and then that's auto boxing, of course. And then once we have it as an object, then we can ask it for its hash code. So that's what we do here. Okay, any questions on this? It's all obvious? Okay. So remember, page 103 is where you can find this. Could probably put a tab on it. So you need to use it. Okay, so there's even more to this reminds me of, so we can look at. There's an @ override. So let's go back and look at that. See how there's an @ override? This is making the compiler check that this equals is actually overriding object equals. And that's a very good thing to check. It doesn't change anything about how this executes, okay? But it does check whether we've made a mistake and misquoted the equals method, which is easy to do, because doesn't it make sense that if we're doing equals on order, we should put order here for the other? That's very commonly a common mistake. But if you do that and you do @ override, it won't compile. It'll tell you why. So you know, oh, of course, equals has to take an object, not an order. It's supposed to be able to check different class objects. It's a little more general than just looking at order objects. Okay, so that's, and it's here we have override here as well. So hash code must override the one in object to satisfy this. So this is just asking for service from the compiler itself. Okay. So that's what you need to have an object parameter in order to satisfy, in order to get our method to actually override the one in object. And we're seeing that here's a trick that we're using here in hash code. We're delegating the value to the ID field or instance variable at ID. So we just turned the ID into an integer, and then we took that integer's hash code. So that's a standard trick for doing hash codes. And we can see we can do even when we have more than one instance variable, we can still borrow their hash codes and combine them, say. Okay, so here we claim that equals and hash code are consistent, which means that if we have equality, then the hash codes are equal, because it's true with the integer case. But we notice that there's no compare to. So that means that we can use hash set of order, but we can't use tree set of order without special trickery. Okay? So if we look at again at this code, you can see we've got equals, we've got hash code, but there's no compare to. Well, we can fix that, of course. Okay, so we've seen that the code that we just looked at required that the classes be the same before it would finally say that x equals y. If you look at the rules for equals, there's no such requirement in general. Okay, so here's the book, page 102. Let's look up what are those rules for down here at the bottom of the page here. They must be reflexive. X equals x is true. Symmetric, if x equals y, then y equals x. Transitive, x equals y and y equals z. then X equals Z, and consistent, they have to return the same thing, and not null. Okay, so X equals null returns false. Okay, so those are the actual requirements on equality, not that they be the same class. And here's another important, well, somewhat important fact about JDK sets. The JDK sets are A and B can be checked for equality, even if one is a hash set and the other one's a tree set. This is a very strong statement. What does it mean? Two sets are equal if their elements are equal, even if A is a hash set and B is a tree set. So that's showing you that you don't have, in general, you don't have to have the same class in order to have this kind of equality. And but of course they have to have some similarity of type, or you would never be able to check this or anything. So in this case, they're both sets. So what we have, we can say that hash set is a set and tree set is a set. So we have a little inheritance tree. I think I can draw it. See if I can draw it. Yeah. Oops, over here. We have hash set and tree set. And then we going up here we have set. And that's the inheritance structure. But this is an interface. So you can see that this interface can't implement equals. So there can't be an equals up here in an interface because interfaces are not allowed to have code, right? So where is it? Well, it turns out that the picture is a little more complicated. There's not the thing that is here first is called abstract set. This is a class. It has abstract methods in it, but it's a class. And then we go up here and we have set at the top. Okay. So this is the hierarchy. So this abstract set can have equals and does have equals. It has this powerful equals that can check even if they're different types, whether the contents are equal. Okay. So that's, so of course we've promised not to talk too much about classes, subclasses, but I want to show you there are, when we bump into them, reasons to use the power of subclassing. Okay. So we're not officially covering this, we're just sort of bumping into it. Okay, any questions on that? Okay, and we could do the same trick for point 2D and point XY. They were very close together, and they both represent points, and so you could easily imagine that a point 2D point could be equal to a point XY point because they have the same coordinates, right? So if we wanted to implement that, we'd have to kind of copy the structure that we have here for the hash set and tree set. We would have to have a class, superclass, and then that would be between the interface and two contending implementations. Okay, so here's a set of orders. We now know that we can use hash set with order legitimately. And you can see that order, this is the ID of the order. So we're creating an order with 600 and then 100 and then 200 and then 100 again. Well, now because of the better equals, these are known to be equal and duplicates of each other. So when we print this out, we only have 3 orders there. The duplicate has been squeezed out. Whereas if we didn't have that equality, those would have been different because they would have been new order. They would have gotten different memory addresses. They would have been 2 objects that have the same contents but have different memory addresses. So they would show up as different. Okay. So this really does make a difference. Any questions on this? Okay, well, obviously we'd like to see a tree set of order as well. Okay, and that means we need to have a compare to in the order implementation. And it turns out that compare to is easier to implement than equals. Equals is the one that's tricky. I think the main reason is because its parameter is generic, as a generic type. But as usual, we would like to use @override to check our work, make the compiler check that we've actually overridden the object method. And we're going to use that other trick too, that we can delegate the comparing based on the integer ID compare. Okay, so here's the equals, same as before. Here's the hash code, same as before, using the integer hash code. And now similarly, we'll do the same trick. We'll take the integer ID, turn it into an integer, then call its compare to on the other one, and thereby get a compare to for this class. Okay. And of course, the toString should return at least the identifier here. Any questions on this? Okay, so here we have the tree set, and we put them in, and again we have a duplicate, but it's found out because the compare to would be comparing 100 to 100, right? So it would be found to be a duplicate. And this being a tree set, we get order for free. So that means we would get 100, 200, 600 here in the orders. Any questions on that? Okay, so we've now looked at a case with the full compare to and equals and so on. But let's go back to a simple case of bank account that has no equals. And what if we want to make a set of bank account? Well, we can't use tree set because there's no compare to. Okay, that's clear. But we know we do have equals and hash code for the bank account objects because they're objects. So that means we can use hash set of bank account. Okay, we have to realize that it means that 2 bank account of the same ID would be considered different, and so you wouldn't squeeze out the duplicates. Okay. So how does object equals work? Well, it just compares the 2 references, the 2 memory addresses. So it returns true only if the 2 objects are exactly the same object. I think we've already said that, but anyway. So you can see that it doesn't depend on the identifier at all. It's the internal identifier. Okay. So we have to, if we want to do a good job of squeezing out duplicates, we have to implement equals and hash code to do this. So it would look something like the code we've already seen. Okay, so here's a different case, a simple student. Again, this is has you can see what does it have? What can we do with this? Assuming these are all properly coded, we see it has two instance variables, and the equals is checking the class, and it's doing the same thing as we did before with order. It's checking the ID. The IDs have to be the same in order for the students to be the same. So the name isn't counted as part of the identity. Okay. And of course, that has to be true. You could have two students with different names, and yet you have to treat them differently. So you give them IDs so that you can be sure that you have a unique identifier for each. Okay. So here, again, we're doing a compare to using the compare to of the integer of the ID. So we have everything here that we need. So that means that we could use either hash set or tree set, whichever we want to. And the only advantage of tree set would be it would keep the identifiers in numeric order. Any questions on that? Okay, so here we could drop equals in hash code. Of course, we can't drop just one of them because then they wouldn't be consistent. And you get sets that just didn't work. You'd drop things in and never be able to find them again. Okay, so we've seen that in lots of cases there's an identifier that is that says which objects are the same and different. Just like a database record has a primary key, which is usually a single field, but it doesn't have to be. Right? And so also if things are equals, then the hash codes have to be the same, but it doesn't have to be true the other way around. Okay, but to cover the ground, we should also consider the case where we have more than one instance variable needed for identifying objects. Okay, so here is a case of that. We have a phone number, and we want to split it up into the area code, exchange, and extension, I guess. And here is, so now we have three fields or instance variables. And we want to say that all three are important to the phone number definition. So you can see that when you create a phone number, you have to say what the three are, and you save them away. And you should have getters for all the parts of it, and maybe even a getter that puts it all together into a string. But what about equals? Now that we have three things. Well, we start off with the same two statements, and we can check the class again, and then put the, set up the reference to the other as a phone number. Now that you know the class is the same. So here's the cast. And then once you've done that, then we can look at the various instance variables. We can, we're looking at the same class, so we can look at all the different instance variables, even for the other end of it. So we just check if the area codes agree and the exchanges agree and the extensions agree, and then say that that's then an equal phone numbers. So how about the hash code? Well, we have various ways, but here's one way. Since they're numbers, you can just take a prime number and multiply, sort of make a high, make an integer of a high base out of it. Or you can take the hash codes of the individual numbers, but they're probably the same thing. And all you have to do is, you can even just sum up the 3 hash codes here, and that would work. It just, it's good for hashes to spread out evenly, and by multiplying by primes, they will spread out better. So you end up with faster hash tables. We'll be studying hash tables fairly soon. Any questions on this? Well, that's the end of that. We want to go on to the next part, which is a different file. Oh, I guess there's an old date on it. Okay, so we've talked about sets, which are very simple, just collections of things, and now we want to go on to maps, which you have had a lot of experience with, but they were called symbol tables. Okay, so just have to rename them. So starting from the notion of sets. So suppose you have this set of student records, and you wanted to find one of those students by ID. You can see if you look at the API for set, you don't have a direct lookup method. The only way you can find things is by going through the whole set and checking them one by one. Well, it's pretty inefficient. So the order n, where n is the size of the set. So we would like to have a better way, and that's what the map interface allows us to do. And it's also exactly what the authors call a symbol table. Okay, so we have a map interface, whereas in the book we have ST as a class. But here, what we're talking about is the API of that class. And they do write it down as an API as well. Okay, so here's another way of looking at maps. I'm sure you saw something like this in 210 for symbol tables. You have a domain and you have a range, and the map or symbol table allows you to look up the range element given the domain element. So typically a lot of them hit different values in the range, but you can have 2 things in the domain which point to the same thing in the range. Okay, so this is a mathematical function, it's the same characteristics. Okay. But you can't have two arrows coming out of the same point in the domain. Each element of the domain has to map to something over here in the range. There can be range points that aren't reached by anything. Okay, so that's what we're saying here. 2 arrows will land on the same range, but one domain element cannot have 2 arrows out of it. Okay, so you can see that we can do a lookup by following one of those arrows. So with employee records, you might look up you're looking up by social security number, or more likely employee ID number, or maybe employee name. And in that case, we have the social security numbers, which do nicely fit in an int, or the string names in the domain, and the employee objects are in the range. Okay, so you can call these lookup tables if you want. Okay. So we can be mapping integers to employee objects or strings to employee objects. And of course, we're usually going to use objects, integers themselves, of course, are primitive type. It'd be capital I integers, more likely in reality. Anyway, what happens when you create a mapping is you're creating a bunch of pairs of domain and range elements. And these are sometimes called associations. Okay, so these are associations define the mapping. So each association has a domain type key and a range type value. So this is just basic stuff. And here's the simple possible kind of map. You have scores to letter grades. So 92 is an A, and 79 is a B, and 68 is a C. Okay, this is a mapping. And the key here is the score, and the range is a string. And we, for example, put an A minus, so we need 2 characters. So we can call this a key value pair, or a pair, or an association. Okay. So it has the pair 92A, and the whole mapping is a set of 3 pairs. So you can say M equals, this is a set. This is one of the associations. This is the other one. This is the other one. So every map can be thought of as a set of pairs in this way. Okay. So this is part of the Java collections classes, but because of the additional complexity, it has to have its own API. Okay. Unless we wanted to just use the set, the notion of a set of associations could be, used. We could say, well, we can use the set, but then we wouldn't have the power of the lookup involved. So we really want an API for map. Okay. So you can see that you can't just say it's any collection of pairs anyway, because you can't have the keys can't have any duplicates. The keys have to constitute a set. So we have a set of keys, and this collection of values. The collection of values can have repetition. So we have a set of keys and collection of values. Okay, so here's the map interface. So you see it has a key type and a value type. So it's generic 2 ways. It has a size and is empty. That's really easy. It contains key. So you just throw in a key type, and you can get, this is the get, this is the lookup. You specify key and you get back a value. Similarly, here's the basic put, which puts a new association into the system. Well, it doesn't have to be new. It could be overriding something that's already there, but it adds a key value. So it overwrites. It should be overriding, really, not overriding. And you can remove a key, and of course, along with its value. You can clear, and you can return the set of keys in the map. This is like the symbol table has a method called keys that does the same sort of thing. And then you can also get all the values as a collection. Of course, it's not a set in general, so it's just a collection of the value type, of course. And then there's a way of returning the set of associations, which are expressed as map.entry objects. Okay. And so you can see it's a set of entry of key and value types. We have, you know, a pretty deep generic specification there. So this is the entry set, so we get all the associations that belong to the map as a set. Any questions on the basic API? Okay, so of course we saw this entry key type value type in the API, so it has to have a definition as well, and this is part of map.java. You can see it just contains the key and the value, so you can get the key or the value out of it, and you can set the value. So you don't change the key directly. You can throw it away and start over, of course. And again, don't worry about this extend serializable. Okay, so how do you actually see these? If you call entry set, if you remember, go back here. Entry set, that's the one that returns a set of entry of these key type and value type. Okay. So you get the entry set, and that's a set. So then you ask for an iterator, and you'll get an iterator over this set of pairs, over these entries that look like this. So you next through them, and you get the map.entries, which are the key value pairs for the map. Okay, now this is not, you don't have this in the books. You have the keys. If we're going to look back here, you know, we have the key set here is very much like keys, but they don't have something that passes back the whole entry set. Okay, so we can add key value pair by using put for key and value, similar to the ST symbol table, and we can look up the range element given the domain element. That's the basic lookup, and we can find all the facts by iterating through the keys and looking up each one with get. Okay, so that's sort of a basic way of doing it that you could use for the STs as well, using keys. And or you can see we can look through all the entries by calling entry set, which is also an iterable, so you can loop through it. Okay, so this is the same slide as before. So this simple example gives us here, this is like the entry set. Okay, so we have tree map and hash map, just like the set case. So let's start off with hash map, and just try it out. It's very easy. Set, just say map integer string hash map, new hash map. You don't have to put anything as an argument there. And then we can put some facts into it. Here are the facts that 92 gives an A, and 79 gives a B, and 68 gives a C. And then we can print the whole thing out just by this way. And this is what you get. You get all the facts. You get the 68 equals C, and 82 equals A, like that. So it shows that the hash map class has the toString method, and then it in turn goes and does the toString of the key and the toString of value and puts them on either side of these equal signs. So you don't have to iterate through any of these collection classes to get this nice little big. You can just print the big object, and it'll be, as long as you've got toString on the elements, you'll get the whole story. Any questions on this? So that's easy. So here we have integer string. But this one we're doing the entry set instead of to see what that looks like. Here we have printing the individual entries. We could print out, there's two ways to do it here. We're printing out the entries, which is this big set, or looping through and individually printing the entries. Okay, so here's the part that we're talking about, the entries. That's this one here. And then the individual entries look like this. Now what's happening here is the hash map has a toString. The entry set has a toString that gives these brackets, and then it calls toString of the entry itself and gets this packet, and that code calls the toString of the key and the toString of the value, and gets these two individual things. So you can see that this is the same as this because they both involve the same entry. Okay, so it's very easy to use because of this powerful output capabilities. Okay, so it's really important to understand when you should use a map. You know, what is it good for? You can hold conversions, social security names. You can think of them as generalized arrays. An array, or you can think of an array as a map. As an array maps 0 to A of 0, 1 to A of 1, and so on. But that's very restrictive because it can only use integers, at least in Java. But with maps, you can use any type. Okay. You can think of they're related to math functions. And you can also think they're related to databases. Okay. So when you have social security numbers to employee records, you could have that in the database table, and with a key, the social security number could be the primary key for lookup. But you can have it in memory with a hash map or a tree map. Okay. Similarly, you could look up books by ISBN or names to inventories and so on. So they're just terribly useful. Okay, so we can see that we have the same need for equals and hash code and compare to. You can see that the basic structure of a map involves the domain elements. And the domain is a set. So when you're working with keys, it's just like working with a set. So you have the same kind of equals hash code compared to need for the elements. You just have to look at the key elements to see what you need. The range elements don't need any of these special functions. They're not involved in the lookup. Okay? So you can see we need equals and hash code for a hash map on the key objects, and equals and compare to for key objects in the tree map. Okay? So the value object can do anything. So it's very common to have integers and strings as the domain type, and then some kind of complicated object as the range type, so that you don't have to worry about it. And okay, so we can see that if we ignore the values, we have a map. All you have left is a domain, and so that gives you a set. So this is the trick that the textbook uses to simplify the world. Okay, so if we look at what happens in the book, that presumably you've been studying in last term, you can see that they start with the symbol tables, which are terrifically important. I'm not saying that this is a bad approach. These are the maps that can do the powerful lookup capabilities. And you can look at the ST API. You see it has get and put, the keys method. And so it's very similar to the simple part of the map API. Okay. So there's just a little bit of coverage in those pages there, 3 pages on sets as STs without values. Okay, so you can see this works for a simple model of sets, but we want to really study JDK sets even more than we have. We want to see how we can do set union and set intersection. You know, all the big, really set crunching methods. And we've seen that sets support set equality, even across implementations. It's pretty impressive. And so even the maps glom onto this by saying, well, sure, since set equality is implemented, we'll give you map equality. So 2 maps are equal if their entry sets are equal. And that's really all there is about a map. A map is completely defined by its entry set, because the entry set has all the domain range pairings. Okay, so there's even more. Let me have a little more time here. If you get a set from map.entrySet, it's not just a snapshot of the map contents, but a live view on the contents. So it can follow changes in the contents of the map. Okay. So similar to the key set part, I guess there should be a capital S in there, but there's a view on the map's domain, and the values is a view on the map's range. So there's this notion of view, and we want to look into this a little bit more. To compare this to the book's STs, there we have keys, which is like key set. If we turn to set of keys, but it's just a snapshot. It's not a live view. Okay. So what does it mean? Let's explore this idea. The element that you can add an element to the main contents. So if you already have a set that you got by calling entry set, and then someone adds something to the map, then you go and look at the entry set again and you find it. So that's adds and deletes. Now, if you just change an element, that wouldn't be different in the 2 things. If we update an individual element, that would show up in the derived set from keys or key set because the elements are all handled by reference. So if we so you never copy an element. You just make another reference to it. And so really, in that case, it doesn't matter whether it's a live view or a snapshot. Any questions on this? I'll have an example here. Okay. Now, this is a tricky thing. So there are limits to it. You know, if you can't, it isn't magic. So yeah, it has to be implemented carefully and keep things honest. So here's an example of what happens. If you start scanning N with key set, and then you delete an entry in M by using remove, just remove of the object, okay? Now, you'll find that if you try to go back to the iterator, you've started a scan, so that means you haven't completed the iterator, you just started it. If you try to move the iterator with next, say, it will throw the concurrent modification exception. So it refuses to go on. And that's because it thinks that it's unsafe. It can't guarantee to give you the right information. So rather than give you stale information or garbage, it throws. Okay, so this is something you can get in any of these complicated classes. They all track what's going on, the modifications that have been done through their API, and throw instead of getting into dangerous territory. Okay. So this is one way it can work. It can work because it is able to throw if it gets into a dangerous situation. Now you might say, what about the textbook approach where you just get a snapshot instead of getting the live view? Well, in that case, you get a snapshot with keys, and then the deletion happens, and you can continue to use the iterator on that collection because it was just a snapshot. It wasn't guaranteed to be live. So you just get the stale data. You get the key value that was removed shows up because it was in the key in the set. So you can see there's a. So you might worry, oh, well, what can you do then if things like it's so easy, you touch anything, it blows up. Well, there are plenty of things that work. Okay, so here's a couple of examples that work. You can set up one set X of maps domain, and then you scan the whole thing to count it, say. That uses up the iterator, so you don't have a live iterator at this point. Then you delete the entry, and then you scan X a second time, and you get a lower count. So everything's fine. So there wasn't a live iterator at the time of the deletion. Okay, so that's one way, and that's a very common case. Another thing is that you can do deletions through the iterator. So this is something you haven't seen because if you look in the book, they say, oh, well, we use iterators, but we never use remove. Remove is always a no-op. And they give an argument for that. But it's in fact very powerful. Because look what you can do. This is another one that doesn't cause error. You set up this set X of the domain, and then you iterate it through it with an iterator I that you got from the set, the full iterator with a remove, and you remove an entry in the base set using the iterator remove method, and you can continue. You can continue to use that iteration because the iterator knew everything about the remove. It remains healthy. Okay? So you can see that the iterator remove is actually gives us more power in working with these maps. So you can see if the iterator's in control of the edit because you're using the iterator's remove method. So you're using you call into the iterator, so it remembers what's going on and can arrange to sort of skip over the part that got deleted. Okay, because it has to be right there when you do it that way. So of course, writing code that does this kind of thing is pretty tricky. But we will be looking at real JDK hash map code in project 2. So you can, the part that you need to do doesn't really involve this, but you can look at the other code and see how it's possible to implement this kind of tricky iterator work. Okay, so that's a good place to stop. You can see that's the end of that. So next time we'll start on lists. So we want to look at the JDK list.